Okay, folks, we're about to start. I'm going to mute the remote end. So if you've got questions, please put them in the chat. And we'll give you an opportunity to ask them. And then after the talk, we will unmute the remote end. So maybe you can ask why. So thank you very much for coming. It's a great pleasure to introduce Chenoa again. Some of you will have seen her public lecture last week. It was more of a public lecture. Today we have a more hardcore technical version. So Chenoa is a project scientist at the SETI Institute, and she is also working with breakthrough listen. In another capacity, she is the project scientist for the cosmic backend of the relay, and the breakthrough listen includes backend of BeerPack, right? So those are the two components of backend to search for techno-signatures as BeerPack of the relay. And I think we're probably going to hear a lot about that. And before that, I think spent a long time in Australia. You touched your PhD in Australia.
I did.
Yeah.
I did.
But now she lives in, well, not quite in Sapporo. But
Yeah.
Sapporo.
Yeah.
And this is, I believe, her first visit to South Africa. All right, Chenoa, the floor is yours.
Right. Well, thank you very much, Oleg, and thank you for having me to be able to come and talk about the work that we're doing for the search for life in radio techno-signatures. So the talk is covering a bit of engineering, a bit computer science, and a bit of the science side of things. So if anybody wants to interrupt me with a question, please feel free to do so. I don't mind. Then we can keep on going. So before I get started, I wanted to acknowledge the other members of our core teams that have been working with these systems. So on the Cosmic team, we are a diverse background of people that are from South Africa, the United States, and the UK predominantly. And I have a team of students that come and go that I mentor on various different projects and pieces of projects with these systems as well. And similar with the BLU's system, that we've got a diverse team that helps me and makes these things work, and I greatly appreciate their efforts onto this. So the two systems that I'm going to be talking about in particular today are both designed to try to answer the question, are we alone in the universe or are we alone in the galaxy, from a standpoint of radio astronomy. So observational astronomy gives us a viable way in which we can explore this question, and we're doing so. So the basis of this talk is going to talk about some of the technical aspects of this, but also some of the scientific challenges and what we're actually doing and seeing in this. So this is a tremendous problem. You may have heard that it is the nine-dimensional cosmic haystack, as in the proverbial needle in a haystack, that we don't know exactly what we're looking for. And there's a lot of different ways that we can explore this space. If we look at what we're currently doing, is that we're mostly focused from a sensitivity standpoint, a frequency standpoint, distance and spatial distributions. We've been trying to explore different transmission bandwidths and how that would look, some different time and repetition rates, but we haven't put a lot of time into polarization and modulations, and those are far more complicated problems. At the moment, there are about 12 radio telescopes around the world that we either have dedicated SETI experiments sitting on them or have been involved in SETI in some regular capacity. And these offer a range of sensitivities, frequencies, and obviously the North and Southern Hemisphere exposure as well. Now we have two different modes in the way that we operate these telescopes. So for our single dish, there's the problem where you have one field of view, you have no way of differentiating objects within that field of view. You might say you're targeting one star, but you've got galaxies, you've got other stars, things like that. And I'll talk about in a second how we handle that data to try to differentiate radio frequency interference from a signal of interest, which is roughly RFI from somewhere else. And then when we have interferometers, these multi-element arrays, there's a huge amount of stuff that we can do that we can't do with a single dish. One is that we could image the entire field of view, and that would give us a high resolution at a spatial scale and across the whole band, but that is computationally very expensive to do in real time in particular. And so one of the things we do is these coherent beamforming, which allows you to use the phase information to target particular objects within the fields. And then you can do that simultaneously, choosing and prioritizing some of those targets. Or you can do an incoherent sum, which allows you to treat each one of the elements in the interferometer as a single dish telescope, and then you're averaging up for a greater sensitivity. So we employ a mix of these different methodologies in the systems. So the way that we handle the single dish case is that we point on source for a certain amount of time, and then we point away from that location, and then we come back to the location, we point somewhere completely different. So we end up with 5 different pointings, but this gives us an ability to kind of differentiate if radio frequency interference exists. It often stays in the telescope beam for these on and off pointings, or at least some of the off pointings and all of the ons. If it's not, and it's actually targetly located towards your field of interest, then it should stay on only in the on-source target beams. And so this is an example of the Voyager signal where we go through and explore this from that way. But the predominant stuff that I'm going to be talking about is the 2 experiments that we do on the interferometric rays, the MeerKAT telescope and the VLA in the Northern Hemisphere. So as you're aware, the MeerKAT is in the Kourou, 13.5 meter dishes, 64 Gregorian offsets. And breakthrough listen user supplied equipment is one of the commensal backends onto the MeerKAT telescope. One of the huge benefits and I think wonderful thought processes of being able to take these copied of data off from the F engines so that we can process them independently of what other research is going on at the time. And so with these multiple systems, we're getting a lot more science out. And so the breakthrough listen equipment is one of these systems. One of the benefits of that is that means that we can put all of our resources mostly in just the compute and storage. And so up at site, we have 104 GPU nodes and 8 storage nodes, which I think recently increased a bit. And so we're able to capture the data and really look in high spectral and temporal resolution. And then vary the experiments based off from what might be of interest at a particular time. So the way the system works is it works autonomously. We're not interacting with the system on a regular basis. It mostly goes about and does its own thing. We use an observational YAML script that controls when to observe and how to run the experiment. So since we're getting the calibrated voltages and we get the calibration data, we take in the data and we store it on NVMEs, which are a fast read-write storage device. And then we can up-channelize the data to about 1 hertz resolution. And then we do a search for techno-signatures, which I'll talk about in a few minutes as to what that actually means and what that looks like. And then what we do is when the pipeline finds a signal of interest, it goes and saves the voltages around certain signals or all of the signals and stores those to disk so that we can go back and look at that data in the future. While it's operating, it's doing 2 things. It's inputting the information that we get from MeerKAT or Soreo of what the telescope is looking at, what frequencies, what's the setup, whether it's subarrays, things like that. And then it's providing information back to us through Slack, so we know what's going on. The other experiment is on the Kolzhi-Jansky Very Large Array. So this is a 27 dish, 25 meters each in diameter. It's one of the only telescopes in the world where the dishes move in different configurations about every 6 months or so. And these antennas split out between long baselines of 1 kilometer to 36 kilometers, giving a wide range of sensitivities to different spatial scales on the sky. Typically, the standard system runs 1 to 50 gigahertz. We only take in 2 to 50 just because of the RFI environment there from 1 to 2 gigahertz. That we need to put a few more things into place before, like an automated filter, because we were able to fill up about 800 terabytes of space in about 6 hours. So not ideal. And so we've been filtering just from the 2 to 50 at the moment. So at the VLA, there are a number of commensal systems. Cosmic is one of them. The real fast system looks for FRBs and pulsars, mostly time variable transients, and they get a tap off from the correlator itself. The V-Light system actually runs a dipole antenna on 18 of the antennas at the focus of the antenna, and they have a completely separate digital stream that goes into the control building and is handled by the Naval Research Lab. And then Cosmic, we actually get an amplified split of the digital signals from each one of the antennas. So it kind of looks like this. So each antenna, the digital signals come into the control building, and then we actually do all of the signal processing, and then distribute that to a compute cluster for the processing for the actual search itself. So that's what this looks like. So we have the amplifiers and splitters up here. The signals come in through optical cables into our first rack of the Cosmic system. The data rates coming in are upwards of 2.7 terabytes per second. And so what we use is these passive devices to split out the signals into 12 independent channels using demultiplexers. And then that goes into FPGAs to do all of the signal correction, frequency correction, because everybody's software loves to call frequency something different, whether it's an edge frequency on the front end or the back end or the central. That would took a few weeks to kind of work out. And then we, from there, distribute through a 100 gig Ethernet network across the compute cluster. So within Cosmic, we are actually doing all of the digital signal processing. We do the computing, and then it runs 2 pipelines, one for calibration and then one for the actual beamforming and search itself. Similar to the Meerkat system, NRAO tells us what the telescope is doing, which antennas are actually online, and then we can then adjust the scripts and the what's being observed and how that's being observed, but it's also running autonomously. And so the script is just telling it what to do and when to do it. While it's running, it's also sending us messages on Slack. It produces calibration plots. It tells us when there's particular problems, if the disk is filling up, things like that. So it gives us a way to troubleshoot the system without actually having to log in, which is really helpful. So what does the system actually do? So there's a lot of different ways that we can think about how we do techno-signature research or SETI. We can look for continuous waves. We can look for pulse signals. Like I said, modulated and polarized is not something that we've explored quite yet. Broadband signals. And then we can do this as just from an incoherent perspective, or we could do these simultaneous coherent beams, and then we could do image plane search. Currently, what the system is in the real-time system it's doing is doing these simultaneous beams. It does an incoherent sum, and then it's looking mostly for continuous wave signals. The target for the system, so what it does is when NRAO tells us or SRAO tells us where the telescope is actually pointing, is it determines what's the size of the field of view based off from the frequency, and then it chooses off of the catalog all the sources that can be in that field of view, and then it picks a number of those based off the number of coherent beams we can run. So on BLUs, we can do 64 coherent beams. On the VLA system. It's either 4 or 5, depending on the mode of operation. And we're targeting mostly stars. So this is a catalog of 33 million Gaia stars that have been put together as kind of a nearby star sample to increase our sensitivity towards these types of signals. But on BLUs, we're also running the Exotica catalog, which was put together by Brian Lackey. And the idea here is let's throw in a bunch of everybody else's favorite objects as well. And why not just look, see what happens. And so those are built into this catalog. And so we're constantly viewing. With the VLA, it always prioritizes the nearest stars. With the Breakthrough Listen system on Meerkat, we're currently investigating what happens if you look in the same field of view, but now you choose a new set of targets each time you look. And so we're not driving down sensitivity from a time perspective or even exploring the temporal domain as much, but more covering number of targets. There are other signal algorithms that we developed within the Breakthrough Listen and SETI Institute research groups. One is looking for things that are kind of like FRBs, but wrong, like inverse sweeps and various things. This is looking for broadband signals, looking at it's called the SPONDAC pipeline. There's periodic signals. So if you wanted to look for signals of any kind of multiplicity factor, then we could do that. And then we have most of our algorithms are looking for these extremely narrowband drifting signals. But there's lots of different algorithms in development that we all have absolutely available. Everything is open source, and so it's all up and available on GitHub if anybody ever wanted to play with it. It's all there. And so everything from post-processing with machine learning to different observational campaign styles to how we actually do the search itself. When I talk about narrowband signals, if we think of methanol masers or masers in general as being some of the most narrowest signals from an astrophysical standpoint, the stuff that we're looking for is closer to what Voyager and JWST and others have put out as these extremely only a few hertz wide signals versus, something that can be up to 0.5 kilohertz wide. With COSMIC so far in the VLA, we have observed a little over 1 million targets as of July last year. And a lot of this is in these particular patches, and that's due to the survey, which I'll talk about in a second. So far, we've observed about 865,000 stars from our catalog, and there's lots of stuff in the field of views from the incoherent sums. As I mentioned, the VLA runs an observatory-led project called the VLA Sky Survey, or VLAS. And this observes the entire Northern Hemisphere from Dec -40 in multiple observing semesters. So it has just finished up its last campaign for the entire survey. It's been going over, I think, 6 years at this point. And we started observing along with this. And so that's why we've been able to cover so much of the sky. With meerkats, we've observed about 500,000 unique targets. You can see where everybody's favorite sources in the sky are, around the plane and probably some other places. But so because we're not controlling the telescope, we're up to wherever everybody wants to point. So we're driving down. If we look at historical techno-signature research, this is transmitter rate, which is a proxy for a number of stars. So a larger population of stars sits down here, smaller populations sit up here, and then ERP is a power detection, like a measure of sensitivity. And so more sensitive is down here, less sensitive is up here. This is where the plane of what most of the research sat before Breakthrough Listen started in 2015, and now we're still starting to push down into these bounds, and Meerkat sits somewhere in here. So we're definitely progressing the field significantly by these systems. Before I go into science outcomes, does anybody have any questions on this stuff? Yeah.
Mine's a little bit further back, unfortunately.
Yeah, that's okay.
For the VLUs backend, you said it, are you getting the calibrated visibilities? So are you using like the L1?
We're getting the stuff out of the FPGAs directly.
So then, what calibration do you do beyond that?
So we save the calibration solutions into record files. But then we can apply those solutions more thoroughly later, but everything should be phase corrected, which is the important thing for the coherent beamforming. If we actually found a signal of interest, we could go back to those solutions and make sure to do amplitude calibration and flux calibration. But for, just trying to find a detected signal, those aren't usually required. Any other questions? Yeah.
What's your channel size?
They're 1 Hertz frequency resolution. Or it's something like 0.96 something, because we use an FFT to do the channelization. And so it's not exactly 1, but it's very close to 1. Yeah, Lama?
Up to us, what is your effective bandwidth?
We get everything from across the entire band because we're getting it off from the FPGAs. We're just distributing it across the compute cluster. And so we still get the full receiver band at the 1 Hertz resolution. Yeah.
Yeah, but it's 2 gigabits. 2 gigabits instantaneous that's different times.
Yeah, so the bandwidth of the VLA in 8-bit mode is 2 gigahertz, and in 3-bit mode is 8 gigahertz. Currently, with the phase 1 system, I can process 1.4 gigahertz in the 8-bit mode, and we're not processing 3-bit mode. I've got equipment on order soon that we hope to then start getting the 3-bit mode data in, but our digital signal processing couldn't quite handle the data rates from the 3-bit mode yet. Anything else? Okay. So science. So the output of the 2 pipelines that we have running on both BLUs and Cosmic is a database of signals that the algorithm detected. And this is 29 parameters about the signal and the observations that we can use to then do some post-processing to filter out RFI and potential techno-signatures. And then we also get these raw voltage files or filter bank files that from each of the antennas, so then we can explore what the signals themselves actually look like. So we can either reform the data, or we could actually image these, which I'll talk about. One of my students at UC Berkeley took some time to go through those 29 parameters and try to figure out what is the most important for when we're doing the post-processing to narrow out the RFI. And what he found by using a principal component analysis, which is a statistical technique, is that the predominant features seem to be the frequency, the drift rate of the signal, and the time in which the data was taken. And so those are the dominant features in which we use for some of the post-processing. Some different areas of research that we've looked at. So one is taking an opportunity when the astrobiology community finds planets of potential interest or potential habitability. We did a case study with K218b in particular because of its continued interest by the astrobiology as being a potential Hycean world. This one is interesting also because from an observational standpoint, we're viewing it edge on from the elliptic plane of the planet going around the star. And so that means that the observations are only blocked, the planet is only blocked by its star for about 2.5 hours. And so for the rest of the 32 days that it's in orbital phase, we are actually able to see it completely. So what we did was we did a campaign with Meerkat and the VLA across multiple different receivers and across multiple different dates, try to cover as much of that orbital phase space as possible. And then I worked with a master's student in India, Shreya Chattery, to build a pipeline to kind of go through this. So all of the data combined, we found 21.6 million candidates that came out of the actual pipeline. And you can probably guess that the vast majority of this is RFI. Like I said, we're extremely sensitive RFI detector. And so what we did is we went through and create a logical pipeline flow of knowing all of the information about the orbital parameters of the planet, knowing when it was behind its star and when it's in front of the star, looking at different days. We can look for these drifting signals within the data. So for example, a drifting signal due to the Doppler acceleration change between the transmitter and the receiver would follow a sinusoidal pattern. So if you observe it on 2 different days, you would expect the signal to be at a slightly different frequency and drift rate than the previous day's data. And so we can use all of those types of logic to try to narrow down to some of the candidates. These were some of the candidate signals that had gone through the entire pipeline. We have essentially just a single bright pixel, not a true candidate. We had some satellite transmission that's a bit periodic in nature, a bunch of random noise that happened to line up. And then this one looked really promising until we found out it was in a single antenna and not throughout the entire array. And so was just an artifact of the instrument, unfortunately, and not a techno-signature. So unfortunately, out of the 21.6 million candidates, those were all RFI. They're all Earth. So yes, we detected people, just not off-world people. The other thing that we did was that since we took the opportunity to put in a DTT anyway, I got a couple hours extra data on the VLA to study, to look and see if there was any suggestion of a magnetic field around K218b by looking at the interaction between the sun and the planet. And this was work that was then produced by Kelvin Wandia at the University of Manchester. And unfortunately, out of the 3 weeks of observations, there wasn't any coherent emission that would suggest that there was a magnetosphere. But was able to put some strong limits so we can continue to observe that as part of the campaigns that they do on the VLA. Taking into account this pipeline, my new postdoc is now gone through and taken advantage of all of this data we've gotten from VLAS to compare all of the Gaia stars in our catalog that have known exoplanets and then see which ones we've observed within the survey, and then looking and following the similar pipeline idea of trying to put constraints on known exoplanets themselves. Another aspect that we're able to do now is a lot of traditional research for techno-signatures has been in what's called the water hole. And so this is around H1 and OH. This is where the most sensitive receivers existed when the experiment started in the 1960s. But it was also philosophically one of the places of interest because so much of our own civilization tends to congregate human and animal around water sources. And so people thought that philosophically it made sense and scientifically it also made sense. But now we're getting to a point in our instrumentation and our computation that we don't have to be so descriptive or prescriptive of where we're actually searching. And so we broadened this search quite a bit. And in particular, with the VLA, we can focus at much higher frequencies. So my student, an intern, Noah, who's now a PhD candidate at UC Berkeley, developed a pipeline to go through and just find all of these signals that were just related to these single antenna blips. We see this in both Meerkat and in the VLA, that they happen occasionally. Looking for removing things that are just spurious noise pixels that happen to be lining up, and then looking for selected actual signals, candidates of interest. So he pulled a bunch of the high frequency data from 25 to 50 gigahertz, and after running through the pipeline, had 482 candidates to visualize. And after that, he found 12 candidates that we investigated significantly further. These were signals originally found in all of the antennas. They're slightly broad in bandwidth compared to what our typical signals of interest are. They were continuous in time, and they weren't known by NRAO as having a frequency of a known RFI component. After investigating, we actually find that it's across the entire sky. They have shown up at other times and sometimes not in all antennas. So it does seem to be a rare form of RFI, although we haven't been able to track down the exact source of it. But since we're next to white sands, who knows? Anything could happen. To take this a little bit further, Talon went and investigated our entire catalog of all of the data that we had taken at these 25 to 50, ran through the pipeline, and had taken the 2 million candidates down to 0. So there's not as much RFI at these higher frequencies that is known, but clearly there is a bunch of stuff that's still sporadic and periodic. So another aspect that we did was that with having the flexibility of building out the catalog, we had a PhD student in Taiwan who wanted to study if techno-signatures would be feasible from galaxy clusters. So the idea here is that if you have lots of civilizations all communicating, that the sum total over the galaxy might be you might be able to pick that up. And so she created a tiling pattern around about 16 different galaxy clusters. And then each one of those coherent beam centers were placed into the catalog. So whenever we happened to be looking towards, or Meerkat was looking towards one of those galaxy clusters or multiples, then it would prioritize and choose those targets. So she's gone and she's developed and built a pipeline to go and look for those. And she's finishing the rest of that analysis at the moment. So unfortunately, so far, we have not found aliens. No big press release at the moment of what we found. Yes, because I probably would want more telescope time. We always need more data. So one of the things, so we're building towards the future at the moment. So one of the things that we're doing is that my student at University of Virginia, Ella, spent a bunch of time creating just an analytical pipeline of removing the very most obvious RFI. So this is everything from one of the telescopes, whether it's Meerkat or VLA, if they have channels that they know has radio frequency interference, Bluetooth, Wi-Fi, farm equipment, whatever it is, it just removes those channels, creates a mask for those, and then also uses the multiple coherent beams. So if the coherent beams are not next to each other, they're widely dispersed, and a signal is detected in both of them, then it's got to be radio frequency interference. It's not sky localized to that coherent beam position. And so it goes through and just removes the most obvious and then puts those into a separate catalog. And so this is something that can be run quite efficiently. Then we take that catalog, and currently there's a couple of people that are building machine learning approaches. So my student at Rutgers, Gabriel, is working on building a clustering algorithm by doing some trained, I think, supervised learning. Not my area of expertise, but he's been working on the Meerkat data at the moment, and then hopes to also move this to some of the cosmic data as well. What we found was when we went through our traditional analytical pipeline, and then we compared that with using the same data on a machine learning algorithm, is that we found two different classes of anomalies. And so one of the things we find is that we can't just say we're going to go through everything in machine learning. With that, we need to think about this from multiple different perspectives, because we're finding different interesting signals in the end of the pipeline. So the other machine learning approach is being led by Peter Ma and Jacob Littman. So Jacob's a high school student that just graduated and is now going to Brown University. And so they're working on the BL use data. They have a small segment that they've been playing around with and designing different algorithms as well. We're also working on some various different imaging campaigns. So in particular, if we find a signal of interest, one of the things that we can easily do is take those voltage files and correlate them and image them. And then what you would expect to see if it's a real signal that it's a point source. And so this is an example using Voyager data on cosmic system, where we de-disperse the signal and then image it with WS clean. And you can see Voyager sits right there as a little dot. And then we're building even further afield. I guess this is not even as far as it used to be, as we're building out these high-speed computer systems using Stellene and a processing kit under Holoscan and these high-powered computers to be able to do real-time imaging and searching across the entire field of view. So there are some of these systems sitting at the Allen Telescope Array. We've done a number of tests, and so this is a really exciting work that we hope to bring out to some of the other systems, including Meerkat and the VLA. So that's kind of a snapshot view of some of the stuff that we're doing in techno-signature research, and I'm happy to take any other questions.
Questions? Remote people, you can raise your hand or something. Let's get Zoom and open. Local people, any questions?
There's one there first. Yeah.
Do you have any idea, like, how far away, like, with our current equipment, like, we would be able to detect, like, ourselves?
So the benchmark that we used is the Arecibo radar signal that was sent in 1974, the message that was sent off the Arecibo telescope. That was about 20 terahertz. With 1 minute of VLA data, I can detect that out to about 320 light years. With the Meerkat, in 10 minutes of data, it was a fraction higher. It was like 600 light years, something like that. So they're relatively sensitive. If we had more dedicated instead of kind of these blind surveys or autonomous surveys, then you can actually get quite far.
Something you sent out, right?
Yes, that was, yeah, in 1974, we deliberately sent out a message off from Arecibo.
About our ambient level of speed, airport windows.
So there was really, yeah, there was actually a really interesting paper put out by Sophia Sheck and collaborators about 5 or 6 months ago that was called Earth Detecting Earth. So if we wanted to detect JWST or Mars orbiters and things like that, they built a whole entire table about equipment that we have and how we would detect ourselves and how easy it would be. So things like the question of if city lights are a bunch of, high-powered light bulbs and stuff like that, can we actually detect that from far away? So there's all sorts of these questions that are posed. I don't remember the exact numbers that they have, but they do have like a really interesting table on that. So I'd recommend checking that out. But there's some really interesting concepts and ideas. And I think the easiest thing to detect us was 2 things. One was the DSN is extremely high powered, on all the time, fairly easy to detect. And the other thing was cell phone towers, although those are clumped in particular regions, and so would make us very directional dependent from a detection experiment. Yes.
So K218B is the program.
Yeah.
So you said that you follow up to look for a magnetosphere. So when that was originally activated, I should know this, but was that done? Did they find molecular something by looking at its transits across its star, or why would the astrobiology community?
Yeah, so when they did the transit, so JWST follow-ups had suggested that there was water in the atmosphere and hydrogen disulfide, I think it was.
Signature.
Yeah, exactly. There was a couple, and there was also what they would consider a molecular techno-signature, so something that wouldn't be normally expected in the atmosphere based off from whether it was depending on the way the chemistry was interacting and stuff. And so that's why it was kind of driven. Whether people agree on the results and stuff, that's still under debate, and how you interpret it because of what they call the line forest. It means that there's potentially multiple molecules that could kind of fit the model. It depends on how you stack it all up. And so that while that debate is still going, techno-signatures is a way to be able to differentiate life or not life easier than sometimes of trying to define what would live in various environments. And so.
And then I have to correct and say then, so obviously in a magnetosphere,
yeah,
that would be kind of another point in favor of perhaps life. Because if you don't have a magnetosphere, then how is this not a blasted waste?
Exactly. I mean, it's very hard because most of these plants are found around M dwarfs, which are extremely active, and the chemical modeling that they do for atmospherics in planets suggests that the constant bombardment, even if you could keep your atmosphere, would suggest that the chemistry is constantly changing, which would make it extremely hard for life to generate because it wouldn't adapt. It wouldn't have time to adapt to the changing chemistry. Yep. Yeah.
Yeah, just wanted to go back to the 12 candidates that you had at the hydrogen.
Yeah.
And you said those are RFI, but unusual RFI.
Yeah.
How did you get to that conclusion?
Because when we went back through the whole database of all of the signals, they're not sky localized, they were everywhere. Most often found in the geostationary orbit, but not always. And when you look at the signals, that sometimes it only shows up in 5 or 6 antennas, sometimes all of the antennas, sometimes half of the array. And so it was clear that it's transitory RFI.
And the plans can be, I don't know, look at even higher.
So there are experiments that have been done using archival data with ULMA. And that is even more challenging because you expect even higher drift rates. You have to de-drift the data before you do the imaging and stuff. But there's image plane searches with using ULMA data that's much higher frequency. VLA has the highest frequency you can observe is 50 gigahertz, and it still doesn't do it very often because the troposphere makes it a bit challenging certain times of the year and stuff. And so what we've been kind of focusing is also driving on the lower end. So like where MegaCat can observe at the less than a gigahertz and stuff as well, and filling out that parameter space that hadn't been explored.
Yes, I guess also this is unchanged on my heart. At higher frequencies, your yield is worse, right? Because everything gets narrower at higher frequencies. You have to do more targeted, right? You're less likely to just get passive.
Exactly. So one of the things that we're doing is building out a more complete catalog, because I think that there was quite often no source in the field. And so we just do a coherent beam at the phase center, and then everything is just kind of, happenstance, I guess, within the incoherent. And so there aren't many coherent beams that are formed at those higher frequencies, unfortunately. But there is still the chance to kind of go back into catalogs and then pick those and then reform coherent beams, but it's after the initial process.
Mention the EHT already.
The EHT? Yeah. No, I hadn't mentioned it. I mean, there's so Event Horizon Telescope, I guess. We've been in discussions about whether we could use it for SETI for localization and stuff like that, but it's kind of impractical from a blind search perspective.
There's an argument to be made here, so put advanced civilization into something around the all of center of the galaxy.
Yeah.
It turns out they don't keep their own data. Seriously, the HC data still doesn't exist.
But you'd have thought that it would have been a very manageable scale, given that the scale
I've got a comment on the question. If you go to your second last slide, just as a plug, I think you were being very modest.
That's probably true.
Yeah, so I can actually comment that this is actually turning into a much bigger effort than this slide intimates. So we're involved in this quite heavily now, and the idea is to use Stellene to, well, for starters, to adapt a transit search pipeline to run on GPUs, but eventually branching out into the full calibration and energy pipeline, reaching all the way back to the correlator. And the breakthrough backend is kind of the ideal test platform for this. Because we can do this with near-net voltages without interfering with the danger of near-net. So for us, it's a perfect development platform, which is why we're involved. And by we, I mean both roles and setting. But there's also partners in France and Switzerland and Germany that are kind of joining separate. And there's also a plan, kind of a more self-contained plan to use this, whole scan with the TART telescope. So to adapt to the TART, so that there's a TART connected to a GPU box, streaming data directly off the telescope onto the GPU box. And that's going to be, the idea is to ship that as an open development kit to universities so they can, play with GPU development using the actual radio telescope that's directly attached to the GPU box. So that's like the bigger.
I asked Luigi last night, can you give me one slide that summarizes what you're working on? That is his MO is being modest. So yes.
Really plans to move the search for city into space.
Yes. So Breakthrough Listen has put together a team of people to develop, to research the possibility of doing a lunar backside telescope. We call it LIFT-3, the Lunar Far Side Transient and Techno-Signature Experiment. Transient techno-signatures, something else. And so we're in development for that. The idea is to go from 1 megahertz to 2.8 gigahertz. So it's quite broadband. Doing beam forming. It's a series of little dipoles sitting on top of a platform. And we're talking to launch companies and stuff. The idea is that we've got a whole series of white papers. You can look up LIFT-3, LFT3 .space, and you can find our white papers. Yeah.
Just another dumb question. Have we actually looked at techno-signatures from our 8 planets, the further ones? And I think there was another planet, potential 9th planet.
Yeah.
Have there been anything?
So no one knows for sure where that 9th planet is, if it exists. So, but as far as stuff inside, so there's, from the perspective of atmospheric science, there's lots of people that are studying the atmospheres of the planets within our solar system. And this is where like the excitement, I think in 2020 came from, of the phosphine detection, which would be a techno-signature from that perspective, because that environment wouldn't naturally create phosphine as far as we could tell. Then there have been searches throughout the decades that have looked for alien artifacts. So the idea is some kind of signal, or for high-powered radar to image and things like that, to find things on planets and moons of planets that could be of potential interest to this community. From current stuff that we're doing in Breakthrough Listen Study Institute, especially on these commensal systems, we're looking beyond the solar system. But there are experiments that do that.
Any questions? Important. We'll start Chenoa again.
Thank you. Sure.